All right. Outstanding. What are we talking about today?
Say fruits and 3 to 5 axis machine.
We are. Perfect. I just checked it. So one time I did this with a class I was teaching. I was kind of proud of myself because I had been teaching that class for a long time. And I was pretty sure that I knew the stuff that the class was about. And I really hate death by PowerPoint. Who else hates death by PowerPoint? The comedian I shared with you at the end of the last class, he does a whole thing on death by PowerPoint. You should Google it, look it up. But so I was going to show off that term. I went into the classroom every day. I said, hey, what's today's class about? Now, it wasn't because I didn't know. It was because I was checking to see if anybody in the room had been paying attention to the syllabus. And I would wait until they would tell me the correct answer for what today's class was going to be about. And then I would proceed to do the entire lecture off the top of my head, using the whiteboard and the blackboard, moving around. And maybe I'd have some props with me, maybe I wouldn't. I got hammered on the course evaluations. It's like, he doesn't even know what the topic is for each day. He's not prepared to teach class. He doesn't know anything about the material. So when I ask you what's today's class about, it's not because I forgot. I am getting old, but not that old. It's because I'm seeing if you're paying attention. But I'm going to go ahead and get rid of the wrong one. Let's remove this. Let's get full screen on this one. All right. And we don't need the projector. And we don't need the screen for now. We may or may not use slides in the future. I have slides for all of the topics we're going to talk about today. I don't think we need them, but if we do, I'll open some up and we'll look at some pretty pictures that were drawn in advance. Is that okay? What I do have, though, is a schedule for what I plan to do and when I plan to do it. Okay, what time is it? We're only 5 minutes behind schedule, and it's only 5 minutes into the class, so it's perfect timing. So 3 to 5 axis CNC machining. We're actually going to talk about 2 axis CNC machining today. Also, before we can talk about CNC machining, so yesterday, whatever. If I say yesterday, I just mean the last time that we talked. Yesterday, we talked about computer-aided manufacturing at the end of the class, right? And how and so that manufacturing is making stuff people want. Typically, when we do manufacturing, we're doing manufacturing with the intent to sell the stuff that we're making because we think the people want it. By the way, how do we know they want it? Well, we believe they need it, but how do we know that they want it? They ask for it. Sometimes they ask for it. Sometimes we only, even when they ask for it, in having dealt with a lot of customers, a lot of times when they ask for stuff, they're not exactly asking for the stuff they need. They're asking for the stuff they think they need. We know that it was the stuff they needed because they bought it, right? And then they continued to buy it again after if there was continuous need of that. But anyway, that's the other topic. So computer-aided manufacturing is using computers to do that. Computer-controlled machining is just one of the tools that we use in computer-aided manufacturing. To understand computer-controlled machining, we kind of need to understand machining a little bit. So I'm going to take the first couple minutes today to make sure that we're all sort of on the same page with the physics of machining and how the machining process works. Is that okay? Perfect. Okay, so we're going to, there's more kinds of machining, but we're going to focus typically on milling and turning as we talk about machining. And so milling is when the tool rotates. Right? And so you get your rotating tool, whiteboard, right? So we've got our rotating tool. If we were like laying down on the bed of the machine tool, looking up at it, and it was a really big tool, or we were really small, like it was like we were in that Honey, I Shrunk the Kids movie or something, right? If we're down there looking up at it and it was coming at us, we might see something that looks sort of like this. And so it's got this shiny thing. Now, if they haven't spun the spindle, right? So the tool spins. And so if we're looking up at the tool, that would be the bottom of it. And so a lot of these spin clockwise. That's clockwise, right? Perfect. So it's going to spin clockwise, and it's going to have some rotational velocity as it spins clockwise. So we probably wouldn't see those individual edges unless we could like shutter our eyelids at exactly the right frequency, so you could make it stop motion. But we're probably not going to be able to do it that fast, because we're talking speeds of 6,000, 10,000, 25,000 RPMs, and the tool gets small enough. But anyway, that's spinning. It would come down towards us. The typical CNC milling machine, you're sitting on the table, your part is on there, and it moves around. Okay, but the cutting happens. So this is what I want to talk. So we've got this vision of what machining is, and we get see the tool plow through the material, right? The cutting happens when the cutting edge of the tool engages with the workpiece material. The cutting edge of the tool passes through the workpiece material. All right, so I've got a couple models, and so this is an example of a turning. Right, so turning is when the workpiece rotates, not the tool. You do turning in a lathe typically. And a couple 3D printed examples of what happens. Let me pass these around. What happens as that tool goes through the workpiece. And so in our turning example over there, we looked at our workpiece here. All right, so we've got two diameters, D1, D2. Two diameters in your workpiece that I'm passing around has got two diameters. So this is the hasn't been cut yet part of the workpiece. This is the ABC part of the workpiece, already been cut. Actually, ABC means a lot of things in manufacturing. Already been cut, already been crashed, already been chewed. If you see a tool holder and I say that's an ABC tool holder, that means it's an already been crashed tool holder. All right, so this here, so what's the difference between D1 and D2? Yes. Yeah. So D1 is the initial diameter. So the difference, if I do D1 minus D2, I get some value, right? And that equals the depth of cut times 2. Because we're taking that depth off each side. Does that make sense? All right, so so depth of cut is one of the things that we get to control. What else do we control in this process? Yeah. Go ahead, Quincy. We control the rate of rotation of the workpiece. If it's a milling operation, we control the rate of rotation of the tool. And so typical units for that are revolutions per minute, RPM. Especially when we're doing engineering problems, it's really good, instead of writing RPM, to write rev per minute, so that we remember RPM just is an acronym for a unit. Yeah. So we can change the depth of cut. We can change the RPM, so the revolutions per minute, and we can change the feed. And so that RPM, now, when we get to the physics part of it, the RPM is important, but what's really important is how fast that chip is moving past the cutting edge of the tool. How fast that cutting edge of the tool is actually moving through the workpiece. And so we call that the surface speed, the speed at which that cutting tool moves through the surface of the workpiece. So RPM is what's the rotational speed of the part. What's the surface speed then? So it's how fast the cutting edge is moving through the workpiece. So if we zoom in on the chip tool workpiece interaction there, that zone where that tool and chip is going through, go ahead. So the units we use are feet per minute. If we're in any other country in the world, except Myanmar and Liberia, no, it's not Liberia, it's Sierra Leone. I thought it was Sierra Leone, not Liberia. Whatever. We'd be using millimeters per minute instead of inches per minute. But it's one of those African countries. But we're going to use feet per minute because it's America. We're going to be feet per minute. Dang it. So how do we know what the feet per minute is? If we know the diameters, we know the feed rate, we know the RPM, how do we know what the speed? Because it's that as we look at the part, if you zoom in, so if we say the tool's here and it's rotating like this, right? The tool's moving in this direction, but all that cutting is happening not really because of the feed motion. What the feed motion does is it puts that cutting edge in the position where there's going to be material to remove. Because once it goes around once, if you don't feed forward, it's already cut that material, right? So it's got to feed forward, and then it'll cut some more material, and it feeds forward, and then it cuts some more material. So the feed rate does not really say how fast the edge of the tool is moving through the workpiece. It tells you how fast the tool is moving sideways. So what tells you how fast the edge of the tool is moving through the workpiece? Yeah. The RPM is certainly part of it, but the units here are revolution per minute, and the units we're looking for are feet per minute. Because engineering's math, right? Just a bunch of word problems, cancel the units. So we need to make the units work to make it work. So how do we turn revolutions per minute into feet per minute? Constantine. So we need to know the circumference, because the circumference is distance per revolution, right? It's length per revolution. Now, most of the, I saw a picture the other day of a guy setting up a lathe, and it was actually a vertical lathe. But usually our lathes, the lathes that we have over here in the shop, they're horizontal lathes. And so, and by the way, that Z-axis of a lathe is always lined up with the direction of rotation. So on our lathe, the Z-axis is the one that's parallel with the floor. Anyway, so this was a vertical lathe, so Z is in the direction you would expect Z to be in. And the, you know how like the jaws go in and out on a lathe? Clamp the workpiece? Well, the jaws were about the size of this table. And the workpiece diameter, I don't know, is probably 12 feet. I don't know, something in that range, workpiece diameter. And it was about 10 feet tall. And the tool block, right? You've all seen the lathe tool holders with the little inserts in them and stuff. The tool block was also about the size of this table. So you can make a lathe be big or small. In that case, they may have been measuring the diameter or the radius of the workpiece with feet. But with the stuff we work with, we tend to measure it with inches, right? So we need the circumference. But when we get the circumference, it's usually in inches. So we've also got to turn it into feet. So what's the factor to turn inches into feet? Correct. Finn gets a bonus point. Oh, sorry. You don't get your bonus point because I won't remember. 12. And so as long as you make the units cancel, you do it right. Now, is there an equation for it? If we Google equation for RPM to SFM, do you think we'll find it? Has anybody ever used an equation to do this? You all have if you took anything to 100. So let's do it. Let's Google it.
this one I want to present. Need to figure out how to do this. Okay. Close, present, share screen, entire screen, share. Right, now we can all, oh, you can't see it though, huh? Now you can see it, right? We can go to the screen. So, S, F, N, G, R, P, P, N. Turning. You want to do turning or milling? Turning formula calculator. Oh, Carbide Depot. So they sell cutting tools. Oh, they don't tell you the formula. They just let you put it in, all right? So there's a 2-year way. Let's get the formula, though. Formulas and charts. This sounds more cool. Machining Doctor. I think is that really what it's called? The Machining Doctor. I've never looked at this website. SFM to RPM formula. Oh, yeah. So he does it right. 12 SFM pi D. Often, you'll see you'll see 4. What is it? 12 SFM pi over D. That's the formula we see often when you Google that. What does 4 equal? It equals 12 divided by pi. Right. So 4 equals 12 divided by pi. And so when you see this, is it calculating the correct RPM? Is it close enough? As we used to say when I worked on the bridge construction crew, you can't see it from my house. It's close enough. All right, so we got some critical factors. So what happens if our depth of cut increases? When our depth of cut increases, the force on the tool increases. Let's just quickly look at that. So I'm going to look as if we were looking straight down the cutting edge of the tool here. Right, so if we're looking straight down the cutting edge of the tool, there's a chip that flows up there. There's my tool. This is my workpiece. The workpiece is moving that way. It's all relative motion, right? It really doesn't matter if it's the tool that's spinning or the workpiece that's spinning. It's just the relative motion between the cutting edge and the tool, right? And so over here, we call this T1. It's our uncut chip thickness. And you guys aren't going to have to memorize this. I'm going to stay consistent with what people do. This is actually T2, which is our cut chip thickness. It won't, I suppose it's not physically impossible for the two of them to be the same. I've never observed it to happen. So there's going to be some difference between T1 and T2, and that's going to be because here is where all the action happens. That's where it stops being workpiece and starts being chip. And so there's a lot of stress and force that's happening at that interface, because at that interface, the grains of the material are deforming and sliding against each other. And so that's all happening right there. So the chip's going off that way, tool's going this way. In order to do this, if we just, slid it over there towards the workpiece, as soon as it touched the workpiece, it would bounce off, right? It would get thrown back. So we've got to have some force pushing this way and this way on the tool to make the tool stay in contact with the workpiece. The workpiece, of course, is pushing back. on the tool. And we're going to assume that this is a steady state. So we're not going to talk about the acceleration of just starting the cut or the acceleration of just ending the cut. But while the cut is happening, those two forces are balanced because it's not accelerating. Does that make sense? So those forces have to equal, and then so you get a force on the tool from the chip sliding along the tool. Right, so there's a force in that direction. The chip is pushing on the tool, and that's part of what's causing the tool to want to move away. Right, so you could break the component, and so if we got a friction force, we got to have a normal force. So you could this same, and so this is like our resultant force, P. Okay, so that's like the P of the tool on the chip. And so you have the equal but opposite resultant force of the chip on the tool. That everybody still got it? Right. And so this same resultant force, you could actually break it down into the components of the friction force, which is going to be aligned with the sliding axis, right? The surface that it's sliding on, that friction is going to be aligned with it. And the force normal to that. You could also break it down into forces that are aligned with the plane where the shearing happens and the force normal to the plane where the shearing happens, because that's the same kind of activity. But all in all, if you have a bigger chip, you have more force. If you have a smaller chip, you have less force. Is that fair? And that's the level at which we really need to understand the physics of machining in order to do programming. Now, what else is going to cause the chips to, or the, so what are the factors that influence the size of the chip? Yeah. So material bulk properties will be a factor. Sometimes hardness, but a lot of times hardness is just because the bulk material strength is different at that level of the material. A lot of times hard materials are hard on the outside. Once you get through the hard bit on the outside, it's actually not as hard. And that's not true with all materials. I'm not a material scientist. I chose to marry one so that whenever I have to know that information, I just ask her. And of course, since she's a PhD in material science, she won't answer. She just says, well, I don't know what the theory says. Unless she's done the experiment herself, she's not going to tell me what the answer is. Okay, but so the other thing that's going to impact how much force it takes, besides how big the chips are, is what the materials are. Right. So, and it's going to be a little bit on what the tool material is, and a little bit on what the work, and mostly on what the workpiece material is. Because when we drew that there was that friction between the tool and the chip as the chip slides on there. So you could reduce the forces by reducing the friction in that area. That makes sense? So you make the cutting force go down by reducing the friction. How do we do that in practice? So one of the reasons we use coolant is it also lubricates the cutting zone. If you can get the coolant to be in the cutting zone, right? If you can't get the coolant to be there, it's not going to lubricate the cutting zone. But the other thing it does is it takes heat out of the operation, and that friction is going to be impacted by the temperature. So how much friction is going to happen in there is going to be, and you've all done some cutting in our labs, right? So you've all seen chips welded to tools, right? No, you will, I'm sure. And so if you can't get the heat out, then that chip's going to weld to the tool. If you can't get the chips out, it doesn't matter how good you are getting the heat out, you're going to jam it all in there and it's going to be stuck to the tool. So it's mostly the material and the size of the chip that's going to impact how much force we have. Good question. A lot of our lay tooling is coated with some. We have a variety of different coatings, and so the purpose of that coating is to reduce that friction coefficient. The other thing we'll do, especially in the turning, so it's interesting because if you're looking at the physics of the operation, a long ribbony chip indicates that you have a good cutting parameters. However, if you're looking at the physics of cutting, not of the chip formation, but of actually doing the work and making parts, long ribbony chips are horrible for you. They wrap around things, they're razor sharp. When you're looking at them, you're just so tempted to just reach in and pull it out of the way. And that's when you lose your hand or your arm or your life. Don't do that. Did I mention they're razor sharp? Even if you stopped the operation, don't reach in and pull the chips out of the way. Use a tool to get the chips out of the way. So what they do on the tool is, so we use coatings to make them more slippery. And we put little bumps on them to make the chip have to change direction. That chip's really hot when that's happening. The temperatures there can be hot enough to melt the material because you see the material weld to stuff. So you make it when you make that hot chip bend, and chips get work hardened, they break. And so those little bumps that you see on the edge of the tools, or when you have the cutting edge, and then there's a valley, and then there's a bump behind it. That feature on the tool is called a chip breaker. The purpose of that feature is to break the chip so that you get little ding, 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 ding coming off instead of long, glorious, ribbony chips that just look like candy or something, or like the mozzarella when you pull the slice of pizza out. You've got to insert there. Was it just laying around, or you just happen to have it? This explains why he's in the class. Go ahead. But I can't see your name thing, Sean. Yeah. So often, when you're getting those long ribbony chips with aluminum, it's because you were too handsy with your feed rate. And you needed to push harder, take a bigger depth of cut. You need to make a bigger chip. Now, of course, when you make that bigger chip, especially with a material like aluminum, so besides the force maybe causing the tool to break, the other thing that happens is if we got our workpiece here, so we'll just assume that I got no side edge cutting angle. So when I'm over here, I've got some resultant force that's sort of coming diagonally this direction from the tool pushing on the workpiece. That makes sense. So some of it is into the board or out of the board, and some of it is this way, right? Because they're orthogonal force systems, you can make the vectors point in any direction you want as long as you got two vectors. So if you model it like this, well, the force, so when the tool's way over here doing that same cut, so before you removed all that material, you've still got the same forces, right? Because that force is going to depend on the material and the spindle speed. The material, the spindle speed, and the size of the chip. How far in you've gone. And so, what's the equation? What's the equation for deflection? So, as an engineer, should you know that? As a mechanical engineer, should you know the equation for deflection? It's a philosophical question. I think you should know that there is an equation and that it could be calculated. And I think at the moment that you need to know the equation, you go look it up. And that's what I always do, because I'm not good at memorizing stuff. Like, so why would I try to memorize stuff? It's why, I loved history class. I hated when they had quizzes that made you memorize dates. Because I could see understanding the order that things happened, which things happened before the other things, and why there was consequences of one thing happening causing the other thing. But I mean, really, the dates you could get up at when I was a kid in an encyclopedia. Has anybody here ever held an encyclopedia in their hands? A few of us. Wait 5 years and there'd be no hands that go up in this classroom about that question. Anyway, so what I do know, what I do remember about that equation is that it depends on, I'm not going to try to write it without looking it up, but it depends on the force. It depends on how far the force is from the support. So we're looking at a simply supported beam here. It depends on the force. It depends on the area moment of inertia of the thing, which depends on like the diameter and the shape of it and stuff like that. And there's something else that goes in the bottom. I can't remember what it is. Yeah, they're elastic modules. What the material is. I think this might actually be the equation, as long as you remember that length is cubed. So the deflection, but don't write this down as the equation. This is my recollection of what I think the equation is. When you need to use the equation, go look it up. But I'm pretty sure this is the equation for the I don't remember B. Deflection, we'll call that a little delta. And so the further away you are, the more it's going to deflect. And it's actually with a cube difference. So when it deflects more over here than it does over here, what's the finished part look like? There are two options. It looks like this, or it looks like this. Which one's correct? A or B? Yeah. Probably B. Who agrees with B? Stand up if you like B. Is Simon here? Is Simon in my other class? Simon must be in my other class. He did not think it was funny when I made the Simon Says joke. So if Simon was here, Simon says put your finger on your nose. Turn around 2 times. No, Simon didn't say. Yeah, so if you're standing with your finger on your nose, you didn't actually get it right. I meant to say Simon Says turn around 2 times. But it's going to look like this, because the more when it gets deflected, it gets pushed away, which means the depth of cut gets smaller. And so actually, if you think about that in a dynamic sense, it gets pushed away, the depth of cut gets smaller, what happens? The force goes down. Because depth of cut is one of the main factors in the size of the chip. And so when the force goes down, it deflects less, right? So it comes back a little bit. But then the force goes back up, so it comes down a little bit. And then the force gets less, so it comes up a little bit. And so if you do this just wrong enough, and you get all of the factors just correct enough, it will scream. Because sound is just vibration. If you get that thing vibrating at the right rate, who's ever machined a speaker? Right, happens a lot in the milling machine when you want to cut through your part. So you lift up off the table and you put it on some supports and you're going to cut through in the middle of it. Well, I don't know if you've ever looked at speaker design, but now you've suspended a flexible material above a rigid material. And so when you do this, the sound waves bounce off the bottom and they start reverberating in there. And when you walk into the machine shop and you hear it screaming, that's typically because somebody set up one of these resonants in there. And it's just vibrating and vibrating and vibrating until the tool breaks, the fixture comes loose, somebody gets annoyed and hits the e-stop, right? All of those things could possibly happen. So I am at this point way over my scheduled time. This is why I made a schedule. so that I would know if I was on time or not on time. All right, I think we've got enough physics of machining, right? It's about making the tool go through the workpiece. It's about understanding that there are. So, what are the main parameters that we're going to control as the manufacturing engineer in any machining process? I mean, of course, we're going to control which machine tool it is, what time of day it is, what color is the floor paint, who's operating the machine. We're going to control all those things. But what are the primary things that we're looking at in CNC machining? Who remembers? Yes. So I'm going to call it feed, speed, and depth of cut. And depth of cut in milling has two directions. We have an axial depth and we have a radial depth, right? So how far down into the part are we going and how far are we stepping over into the part? And so our feed, speed, depth of cut really translate into a tool path. So it's the path the tool takes through the workpiece material. And when I say speed, I am 100% always saying SFM. Speed in machining is 100% always surface speed, except when it's RPM. But if I mean RPM, I'm going to tell you in revolutions per minute, or I'm going to say spindle speed. So if I say spindle speed, that's going to be RPM. If I just say speed, I just mean the speed the cutting edge is moving through the workpiece material. And that's because the physics are based on how fast the cutting edge is moving through the workpiece material, not on the rotation. And as you change the diameters, speed changes, right? Same RPM, speed changes with diameter. When diameter equals 0, what's speed equal? Zero. So especially in turning, we like to do this thing called constant surface speed, because the tool actually wants to have a constant speed moving through the material. If you're facing off the front of the part and you're using constant surface speed, how do you keep the surface speed constant? You increase the RPM as you get closer to the center. When you get closest to the center, you would have to be going infinite RPM to maintain a constant surface speed, right? So there's another key parameter we use in CNC machining. We call it the clamp speed. That is the RPM that we do not want to exceed in the machine tool. Let's think about, I'm going to take 2 more minutes on this topic. Let's think about our turning exercise, right? So we're turning apart in the lathe, and let's get inside the lathe. I don't recommend this, don't do it at home, but when you get inside the lathe, and you stand back there where the tailstock would be, you look at your workpiece. Let's say we haven't started cutting yet, right? And you've got, if we have a 3-jaw chuck, and so our chucks are all hydraulic chucks. So we've got some hydraulic pressure. There's some pistons that are pushing these jaws with some force, let's call it F sub H for force hydraulic. And all 3 of those have to be the same, right? If they're not the same, it's accelerating. And we don't want it to be accelerating. We really don't want it to be accelerating sideways through the lathe. Axially, we could have it accelerate. Sideways, bad. Leads to loud noise. Loud noise in the machine shop, bad. Except when you're focused on the machine, when you're worried about what's going to happen, the side of the machine, and they go, and I scare you. I don't do that anymore. I decided that was bad too. But when you slam on the side of the sheet metal on the machine, man, does it make people jump. Not recommending this behavior to anyone. Anyway, if FH is too small, so when we out here somewhere in space, so remember we got a lever arm, I'm not going to draw that. We're going to be applying some cutting force, and let's say some of it's in this direction and some of it's in that direction, straight into the board. because we can have any two vectors as long as they add up to the resultant vector, right? So some of it's going to cause the part to want to deflect. There's a formula, we can figure out how much it's going to deflect, right? Some of it's going to want to cause the part to move into the spindle. What keeps the part from moving into the spindle? Friction. What's friction equal? Friction equals mu times n, right? Friction force, and I mean, it doesn't always, that's the most it could ever be. That's the most friction we could have between those two surfaces is mu times n. Now, before we start spinning, F equals n. FH equals n, does that make sense? What happens as soon as we start spinning? As soon as we start spinning, what do these want to do? As soon as we start spinning, we get acceleration. We get force in that direction from each of those due to centripetal acceleration, right? Faster we spin, the less clampy we get. It was this class, I don't know, a decade ago, a little over a decade ago, the new TA. TA had some training. Have you ever had just enough training to be a little bit dangerous? Yeah, we've all had just enough training to be dangerous. So the TA had some training. There was a very specific lab exercise that they were supposed to do. In fact, it was about understanding deflection better. So we're in the big lathe, 30 horsepower, 6,000 RPM spindle. We're in the big lathe. We had a little tiny 1-inch material we're clamped in there because, well, smaller than 1 inch is kind of small, and bigger than 1 inch is kind of more expensive. So we got our 1-inch material in there. We're going to turn it down to like 0.8 inches. And then we're going to have we're doing something to alter the chip load. So the chip load is like how big is the chip, right? We're doing something to alter the chip load. I think it was change the feed rate. That's the most obvious thing to change. So you keep the depth of cut the same. So in a perfect world, if there was no deflection, all the parts would be the same diameter. Change the feed rate, they should still all be the same diameter, except you can take the deflection into account. So it would machine a little bit, then it would cut it off, and then you can pull the stock out. Actually, it was a bar feeder, so it pushed the stock out automatically. That part was automated. And then it would do the next feed rate. And so the objective of the lab exercise was to note what the feed rate was, measure the diameters of the parts, and see how they changed with regard to feed rate. Seems like a reasonable experiment to do to sort of drive home that point. Yeah, well, so it was making some bad noises, but since the TA just had enough training to be dangerous, he didn't understand what the bad noises meant. But the parts were not all the same length. As soon as the second part is not the same length as the first part, what could the problem be? Could be you didn't run the same program 2 times, right? Could be in between running the first part and the second part, you didn't pull the stock out far enough. So it could be you ran a different program. Could be the stock wasn't actually there to cut off. Or during the running of the program, you moved the stock. 3 possibilities. I can't think of another physically possible way to have the second part not be the same size as the first part. And then the third part was a different size. And the fourth part was pretty close to the first part. Then the fifth part was even smaller. What I really, because I walked by the room, heard the noise, knew something was wrong, came in and hit the e-stop on the machine. That's the problem with just a little bit of training, enough to be dangerous, right? And I looked at the parts, I was like, what the hell are you doing? They had 12 parts piled up. They didn't understand, right? But it was all because of this. So there's a couple ways to fix it. reduce the mass of the jaws, right? That'll make them open up less. Reduce the spindle speed. That'll make them open up less. Increase the hydraulic pressure. There's a little gauge on the side of the lathe. You can change the hydraulic pressure. His big problem was the person before him was cutting plastic. When you have a lot of hydraulic pressure on plastic, you squishy it, right? And so they didn't want to squishy their plastic, so they turned down the clamping force and controlled their speeds, and they were probably using smaller jaws. We also had brand new jaws, never been their jaws were huge. But anyways, so y'all, when you do make that mistake the first time, you'll at least know what the problem is, right? Right? Because everybody does it. I've made parts and I said, oh yeah, the part moved. If you're watching real close, you see the part move and you hit the e-stop. Because who has not ever hit the e-stop on a machine tool? First time you go to the lab, find a machine nobody's using, and practice. And pop it out. So you twist it to make it come back out, and then stand there looking at it, and have one of your friends sneak up behind you and say, "Bang!" and practice. So here's my advice when we're operating the machines. If it sounds like a helicopter, and you are not intending to be doing an interrupted cut, and it's the lathe, it sounds like a helicopter, you're not intending to be doing an interrupted cut, that means you're cutting the jaws. You're not cutting the workpiece anymore. Go ahead and hit the stop. If it makes sparks and you are cutting aluminum, just go ahead, hit that e-stop. I think it's a passing notice out of the law. I should stop. Sorry. You get the idea. If it makes a bad noise, how do you recognize a bad noise? You'll know. Okay, but I am way behind schedule, so what are we going to not do? What time is it? 49. 49 is supposed to be almost done with the NC code programming exercise we're going to have you do. We're going to skip that. We'll do that at a later date. Then we can get back to, all right, so just quickly, I'm going to spend from now till 10 o'clock talking about NC code. And I'll give you homework. I'll give you homework to do the NC code programming exercise. It's a little bit more work for me because when we do it in class, I can just draw the thing on the board and then you guys can use your piece of paper and just do it. And when we do the thing as homework, I actually have to create an assignment and put it out there. But for y'all, I'll do that. No, we're going to do the NC code in class after I explain it just a little bit. Everybody's got it, and we'll do this in groups of how many people we got? 2, 5, 9, 11, 12, 13, 14, 15, 16 people. So we'll find groups of 4 when we get ready to do the exercises, impromptu groups of 4. I'll have you together do that. But let's just talk about, so we got some basics of machining. We sort of understand machining. We are not yet machinists, but we know that we need to have tool paths to control the machine tool, and we need to know the physics of all that stuff, right? Okay, NC code. Machine tools move 3 ways. All CNC machine tools that I have ever encountered move 3 ways. They move from, and by move, all right, 4 ways. They all also rotate their spindle. Okay, discounting the rotation of the spindle. So I'm talking, if we're looking at Cartesian coordinates, they move 3 ways. What are the 3 ways? They're not X, Y, Z. The 3 directions they move, sure. But they can move we could have more than 3 axes. We could have X, Y, Z, and then we could have rotary axes. We could have 2 or 3 rotary axes bolted to each other. So we can get all kinds of crazy motion out of it. So it's not the directions that they move I'm talking about here. It's the modes in which they move. So when I say move, I'm really talking about the tip or the cutting edge of the tool and how we're going to translate that in the space to put it where it needs to be to remove the material. So let's say this is the tip of our tool. And then so we're looking down on the workpiece at this point. So here's our tool. Here's the center of it on the bottom. So the center of the cutting edges on the bottom of the tool. So about the tool, we know its diameter. And of course, half that diameter is the radius. Is that correct? When I talk about radius with regard to a tool, if I'm looking at it in this direction, so the side view, so this would be the diameter now, right? And if I say radius, what I'm usually referring to is any radius that's intentionally on the corners of the tool. So if I say the tool's got a radius of this, I'm talking about that. And it's usually going to be like 30 thousandths of an inch, 15 thousandths of an inch. Maybe it's going to be designed to not have a radius. As soon as it touches the workpiece, it's going to have a radius, right? Because that sharp edge is going to wear out fastest. All right, so I always say, and so when I'm doing math that requires the radius in this direction, I say half the diameter. So it's half the diameter times that, rather than say radius, just so I don't confuse myself, because, well, I'm getting old. I got to always use the same terms. So I'm explaining my terms to you. All right, so we're in there, tools like this. So we need to give it a command to spin the spindle. And spin the spindle before you move the tool next to the workpiece. Just do it. If the spindle is spinning and you inadvertently run the tool into the workpiece, the tool has a chance to survive. If the spindle is not spinning and you inadvertently run the tool into the workpiece, the tool breaks every time, no exceptions. People say, and if anybody's got Etch-a-Sketch machine or manual machine experience, will know that you can bring the tool over and you can touch the face of the workpiece and you can say, all right, that's where the face of the workpiece is, without it spinning. You can do that with the controls on a CNC machine. You get like that jog handle. We've all used the jog handle. And so there's clicks on that jog handle. So for each click, it goes a preset distance. You select that distance by telling it how far you want it to go. So it could be a 10,000th of an inch for each click, or it could be 100th of an inch per click. And so that's a big difference in range. There is no force feedback. It goes to the position you told it to go to with all of the force available in servo motors that drive the spindle or drive the axis. So it'll move to that spot. And it'll move there with thousands of pounds of thrust behind it. So that's why in a manual machine, you can bring the tool over and touch the workpiece. In a CNC machine, you can't. All right. So it's an aluminum part and a fairly durable tool. And it's a big tool, not a little tiny tool. And you're in the 1/10,000th range, and you jog over and it touches it, it'll probably just deflect the tool. It probably won't. So yeah, there's exceptions. But ain't nobody jogging over there in the 10,000ths range. They're always jogging over there in the, the 10th of an inch range or something. So, all right. So we need some commands to do things like spin the spindle, do things like turn the coolant on and off. If it's a lathe, tell it what is the clamp speed. We need these commands. And so the language that the machine tools understand, we call it G code. We call it G and M code. We call it MC code. And we call it code. Did I spell code right? Okay. The last one by itself looked weird. And so if I say, did you load your code? All right, the reason we call it G code is many of the commands, since it's a text-based language, who has zero experience programming a computer? Nobody. Perfect. So it's a text-based language. Most of the lines of text start with the letter G, or most of the commands start with the letter G. And so like G00 tells it that for all of the move commands I give you from here on out, so all of the X, Y, Z coordinates I give you from here on out, once you get there as fast as you can. We call this rapid. As you remember on the machine tool controllers, there's a button where you can reduce the rapid rate, and it's by percentages. So you go 100% rapid, 50% rapid, 25% rapid, 5% rapid. Not all the machines have the same rapid. So we have the mill drill center, the boxing machine that's right in front of the big lathe in Washburn 108, 2,000 inches a minute rapid. The mini mills, which you used in M1800, 600 inches a minute rapid. So 25% on the mill drill center is like 100% on a mini mill. So you got to know which machine you're using. You got to understand those things. But it's going rapid from. Here's the other thing: when you get a command to the machine, it does not care where it is. It only cares where you told it to go. So we give a G00, let's say, it's a G00 X1 Y1. I'll put decimal places there. We'll talk about it in a minute. It's going to move from wherever the hell it is to that location, regardless of what's in between it and the location. And we'll talk about path in a second. G01 is linear move. And so to do a G01, so with a rapid move, you just have to tell it where you want to go. And then any more, so X2, X2, Y5, Z minus 1, any more coordinates that you give it after you've told it a G00 will continue to be rapid moves until you change the mode of motion. So rapid is sort of that first of the three ways that machine tools move. Move rapid. They move in a linear fashion, and with a linear fashion, they move to the point you tell it. So if I do a G1 here, so you can put the leading 0, or a lot of people would just say, oh, we did a G1. G1, G01, equivalent. Our machine tools don't care which one you use. Some machine tools do care which one you use. So it's always correct to do G01. But if you think you can say, oh, we did a G1, people know what you mean. So this will move. So if these two lines are at one after the other, well, now we have a known starting point, right? It's going to move from this. Well, we don't know what Z is. So Z is whatever it was when we ran this line. But we have a known starting point. The X, Y are going to move from 1 to 2 and from 1 to 5. And it's going to do that in a straight line, or as straight a line as the machine tool can manage. Now, with rapid, we don't know what the path is. Actually, we can figure out what the path is, but we don't control the path. With linear, we tell it the path. But the other thing that's different here is we have to tell it how fast to go. So we have to go to feet. And so in English units, we're going to use inches per minute. Typically, so F, I don't know, what material you want to cut? Aluminum? Okay. So aluminum. So up here, before we did all this, we're going to start the spindle. S. What machine tool do you want to use? Well, which machine do you want to use? Like the super mini mill, the M2, one of the mini mills? Use the mini mill? All right, S6000 then. Anybody know why I picked 6000? Because that's as fast as it goes. And with aluminum, you want to spin that tool as fast as you can. with any of the tools we own, at least. If you get big enough tools, you got to slow them down because that service speed goes up the bigger the tool is, right? So I got S6000 M03. M03 spin clockwise. Spin clockwise. I don't know. Just Google it. M code. M03. I did remember right. So I don't think that engineers should memorize G&M codes. I mean, we're going to go through a couple of them right now. Here's why. Unless you are the engineer, well, I suppose some of them, but even they shouldn't have to be told to memorize them. The ones that you use, you will remember. The ones that you don't use, you can know that they exist and you can go look them up. In fact, on most of our machines, if you look just under the controller, there's a sticker that has a listing of G codes and M codes. So that's why we use G and M code, because commands that do things like turn the spindle on, turn the coolant on, those are prefaced with M, and G is about moving. Typically. Turn it off. Okay. So G1, G2, all right. So we got to tell it how fast. I don't know. 6,000 RPM. It's in a mini mill. Let's see. It's like a half-inch end mill. I don't know. 190 inches per minute. I don't think we'll. Depends on what our depth of cut is. Depends on how much material we'll remove it. But I don't think we're going to stall the spindle yet. Yeah, aluminum with a mini mill with a tool over a half inch or bigger. You're at risk of stalling the spindle with the cutting force that the tool can handle. Tools smaller than that, you're at risk of breaking the tool typically. Especially at 6,000 RPM, that's probably it's past the peak on the horsepower curve on the mini mill when you get there. All right, but this you got to tell it how fast to move. It's going to move in a straight line. You can tell how fast. The third way they move, G02 or G03. These are arc moves. So on an arc move, you got to give it an endpoint, a feed rate, and a radius around which it's going to arc. Does that make sense to everybody? And so with knowing this, you can now program any shape. You can now make any shape manually programming the code on one of our hog mills. As long as you know how to start the spindle. I mean, I suppose you should know how to stop the spindle. How do you stop the spindle? Well, that'll stop the spindle. But how do you programmatically stop the spindle? It is M05, but what if you didn't know that? Oh, it says it right on the. Well, you can't see it anymore, but it does say it right on the screen. That will actually maybe work. Some machines it will, some machines it won't. The risk is now you've got a servo motor that's doing everything it can to keep that spindle from rotating. And the controller doesn't know. It's right. I'm going to keep that spindle from rotating. I think for this reason it would alarm out. But there's an M command to lock the spindle in place, which is doing exactly the same thing as setting the spindle speed to 0. And people will think, oh, I will set that spindle speed to 0. I'll use that servo motor to hold the tool in place, and then I can use my wrench and I can change the tool. Don't even have to take it out of the spindle. I change the tool. So here's what happens. So the way that servo motor is going to correct for it, if you apply too much force and it decides I'm too far out of position, rather than try to counter you and move against your force, it will do one rotation and get back to position. And your hand's still on that wrench, it'll also do that one rotation, but it won't pass through the spindle very well. Or the wrench will come off and hit you in the forehead. There's all kinds of ways to die. So yeah, I think for that reason, a spindle speed of 0 will cause the machine to run out. But I'm not going to say no machine will do it, and that may be the way to lock a spindle on some machines. And so the arc, leave it a radius. Okay, so all right, here we go. Form into ad hoc groups of 4 people. Each group should have at least one piece of paper and access to Google G&M codes. All right. You can move your chairs around. I'll give you 47 seconds to move into ad hoc groups of 4 people. Did I give you enough information yet? No. So I'm not, what's the word? An artist, nor am I a drafts person. But does the sketch convey the information I intended it to convey? There's sort of a box. It's 4 inches by 4 inches. It's got a right angle corner here. It's got a corner with a radius here, a corner with a radius here, and a corner with a radius here. So G00, rapid. G01, feed, and G02 or 3, this is clockwise. This is counterclockwise. So when we write this program, we program for the center of the tool. So if this is 0, 0 in our coordinate system, so if that's 0, 0, then this point here is what? 0, 3.5? All right, so we're all on track there? Okay, perfect. Now we've got our tool, and it's over here somewhere. And what do you want the diameter of the tool to be? What's the maximum diameter the tool could be? The maximum diameter is 1/2 inch. Is it? It's actually 1 inch, right? Maximum diameter of the tool would be 1 inch, because a 1 inch tool could possibly fit in this radius. All the outside radiuses doesn't matter, but this inside radius limits us on tool diameter. Let's call it a 1/2 inch tool, okay? So first thing we got to do is, so you're gonna, as you're in your group together here, you're gonna create a G code program. You're gonna want to start the spindle. Move to a point here that is above the workpiece, but lined up where it could cut the workpiece. Move, so start the spindle, move above part. And so any program like this, the first thing you do is plan what are the things I want it to do, right? And then you can go fill in the codes. And filling in the codes here is really looking it up in a cookbook. And there's only like 3 codes that you're going to need to use. We won't use coolant. But if you want to use coolant, it's MO8 to turn it on and MO9 to turn it off on our Haas machines. If you want to use coolant. Some caveats of G-code programming. You can have a bunch of G's on the same line. You can only have one M on any given line of code. So only one M code can execute per line of code. Let's see. I think. Oh, so we're going to move over there. So using a 1/2-inch tool, let's cut a 1/2 inch deep. Okay. So we're going to move to above the part. We're going to move down so that we can cut a 1/2 inch deep. And we're going to trace this path around the part. Then we'll move back up. Okay, so that's our plan. So this is, I don't know, what's it, 16, 20 lines of G-code. You guys can make a program that you think will make this tool cut this outline. As we start this, when I got introduced to CNC machining sort of as a thing to do, I was a graduate student. I was doing my research in measurement uncertainty, so not so much in CNC machining. But we got all these new Haas CNC machine tools, and they had some training at the Haas distributor to teach people how to use them. And they had a couple extra training spots. I was like, ooh, I like new stuff. I want to do it. So this is my first experience learning how to program a CNC machine. So I'd seen them before. I'd used a little bit, but somebody else set it up and did the programming. And they said, all right, Toby, you stand here, you press this button. When the machine stops moving, open the doors, take the part out, put it over here, put the next part in, close the vise, close the door, press this button, and wait. That was my extent. So I had become a CNC operator before that because there were parts that I wanted. I got somebody else programmed for me. But my first experience, go to the distributor, sit at the conference table, there's a whole bunch of people in the class. The expert, the guru was going to teach me. I was going to be a genius. I was going to know this stuff. And we spent 3 days doing exercises like this. In fact, this is exactly the first exercise we did. 3 days in studying the manual and learning all the G-codes, memorizing the G-codes, because he was into memorizing stuff. And I'm sitting there thinking, because you're going to do some trig, right? Some of these programs you have to do some trig, maybe not this one. But you're going to do some math. I was thinking, oh my God, I'm going to be so rich. Because leading into this, I was kind of a software guy. Actually, my job title at the time, besides being a graduate student, was senior software developer. I'm going to be so rich because I could write a computer program that could do all this math for us. And I'm sitting there at that conference table, and I invented CAM software. Unfortunately, it was 2001, and somebody else had invented it in 1983. So I was not first to market. But man, and the guy teaching that class, he did not mention the existence of CAM software. He didn't believe in it. From 1983 to 2001, he believed that you couldn't program a machine if you couldn't program it manually. I don't believe that. And this is going to be the only manual programming exercise we're going to do in the class, unless your project requires you to do some manual programming, which it might. I have made many parts that I programmed manually. It's easier to program them manually than it was to use the CAM software that was available to me at the time. I've used programs like Microsoft Excel to basically be CAM software, to do some repeated cuts and to make the lines of code by copy and paste and all that kind of stuff. So your project may involve doing some of this, but I promise you, you'll have to memorize G-codes. The ones that you need to know, you will learn just by having seen them come up on the screen. But you should be able to look at a G-code program and look through the code and understand what's happening. And you should recognize when there's a code you don't know, you could go look it up. All right, so that's the purpose of this exercise. It's the last forced T-code programming exercise unless your project requires it. All right. How much time do you think you need? Because I originally budgeted 35 minutes for you to do this. Oh, shut up. No, be quiet, Siri. And we don't have that many minutes left, and I've still got a couple other things to do. So what do you think, 15 minutes? All right, perfect, 15 minutes. And while you're doing that for 15 minutes, I am going to finish up the people watching at home. I will zoom in on the figure. I'm going to finish putting you in your roots. Sure. You should assume the top plane of the part is 0. Z0. As long as you know what you've assumed, any assumption will work for this exercise. We're not actually going to load this code on a machine and run it today. What was the question? You so on our Haas machines, you could actually tell it to use inches or millimeters, and the smallest increment that it accepts is 1/10,000th of an inch. 3 zeros and a 1. Yeah. In machinist speak, that's a tenth. It'll be a right-handed coordinate system, so Z positive is up. Yeah, so x, y. So x is positive in that direction, y is positive in that direction. Let's go. Go ahead. Yeah. Sure. Yep. The radius you put in is the radius the center of the tool has to go through. Good question. Very good question. If I gave you the manual, you could have read that. But I wanted you guys to consider these questions as we did this as part of it. So perfect. Sure. All right, so you get 103, 600, stage colon. All right, so you're moving to some position. You're moving down in Z. Yeah, I'm not checking the numbers. I'm just sort of checking the idea. We go through the numbers all as a group. That's fine. Yeah, so if you put a feed up here, it'll keep using that feed unless you change it. So yeah, that's something we'll go through. But it looks like you've done the right steps. We'll give it a couple minutes for some other people, and then we'll review it all together as a group. You done? You guys pretty close? You guys done? You guys are done? All right. Let's so pretty close is close enough. What's your first line of code? They say S6000 MO3. Is that okay? Even if it's not exactly what you have? Does anybody think we should have something else first? Okay, let's do that then. S6000 MO3. So we started the spindle spinning at 6,000 RPM. Now, what we have assumed at this point is that the tool is in the spindle, right? And so there's M codes that'll tell it which tool you want and load the spindle. It's MO6 to put the tool in the spindle. We've assumed that. We've also made another assumption. Well, all right. What's the next line of code? What's the second line of code? This group over here. All right. So MO8. Anybody against that? Oh, you know what? So our coolant pumps, there's a check valve right at the pump where it pumps into the hose that goes up to the spindle, and those check valves don't work anymore. I mean, the machines are old. So the machines are 2001 vintage, those mini mills. So the check valves are unchecked, and so the coolant drains back down into the tank. So with an old machine, I don't mind starting the coolant up here because it won't actually be spraying for a little while. But yeah, I like your idea because you can't once the coolant starts hitting the spinning tool, you can't see anything. So I like your thought. And when it's a nice, brand new, well-maintained machine, you can do that. But what should we do after we turn the coolant on? What's next? What do you guys got in the back? X minus what? Y. Anybody dislike that? We should assume the Z0 is the top of the part here, so 0.5 is half an inch above the part. Are you sure? Anybody not like negative 0.5? You guys don't. Why don't you like it? Because you don't know what's there and you're rapiding, right? So we'd rather feed to the cutting position. So I liked it when you said 0.5, as long as we do another line over here. So what's the next one? G01? G01, and we can do Z minus 0.5. And then we have to tell it to feed. How fast do you want to go? It doesn't matter. 10, which is a minute. But we should be assuming that there's no material there when we're feeding down. But we always want to feed when we get really close to the part. It just doesn't move. It only moves the one you put on the line of code. And just the feed rate also. It will continue feeding at 10 now unless we give it a new feed rate. So that's modal. And it will continue doing G01 now until we tell it to do something else. So we're down at the cutting depth. Is this the right location? Does everybody agree? We're at minus 0.5 and 0.5. I like it. Or yeah, 0.25. That's what I meant to say. All right, so what's next? What's next? So RY is at 0.25, right? So we just need to do X 3.5. We could feed faster now that we're not moving down, though. I always like to feed a little bit slower when we're moving down, so maybe we'll do F50. Oh, I got to remember to put my decimal places. Even if I don't put a number after it, the Haas controller, if there is no decimal point in the number you give it, and it's a G number like a feed rate or a location or something, it will assume you mean the smallest increment it has. So it will assume if I did F50, with no decimal place, it would assume that I wanted the tool to move 50 10,000ths of an inch per minute. And so if you've ever been there watching the machine, it says it's feeding, but it's not moving, that's the mistake you made. There was a decimal place missing. All right, so we're here. What's the next line of code? We'll do this really quick. Yep. Is that correct? Yeah. So why is 0.5 wrong? Group in the back. It's because we're programming for the center line of the tool. When would 0.5 be correct? 0.5 would be correct if before you put that line there, you said maybe on this line where we're moving. You really got to do it somewhere else. You have to turn on what's called cutter compensation. When you turn on cutter compensation, you actually program for the edge of the tool, and you make the machine tool keep track of what the diameter of the tool is. But if you don't have cutter compensation turned on, you're programming for the center of the tool. And you have to be moving sideways to turn on cutter compensation. And you should do it when you're not like crashing into the part. So we should have done it up here somewhere. But yeah. So as we were approaching on this line, we should have turned on cutter compensation. Then we could have programmed for just the radius that was on the part. Way easier to write the program manually when you do it that way. All right, but since we're programming for the center line, you can come in if you want. You don't have to stand in the hallway. So next, we're going to come here, right? We're going to come around here like this. We're going to come over to here. And so if you did this line correctly, you're going to do this one correctly, unless you just screw up the math on the geometry, right? This one is a tricky one. So what's this point right here that we get to before we start the arc? Yeah. X 0.25. Is that correct? I mean, I know you guys think it's correct. What does everybody else think? Anybody have a different number? I kind of like it. X 0.25. And so what's the next line after that? And what's the radius? So if we do a radius of 0.25, so if our radius is 0.25, the center is going to end up over here. And if you went 90 degrees around that radius and you went 0.25, then your y would have to be 0, or your x would have to be 0 at that moment. And your y would be, so you went immediately to the arc. Anybody not go immediately to the arc? So when we're here, we're not at the point where the tool can make the arc yet. We need this point to be here before we start the arc. So you guys did it correctly. Well, I don't know if you get the right numbers, but you understood the idea, right? So we need this point to be here before we can start the arc. Then that point's going to be here when the arc is done, and you have to have a segment out, and then you go up here. Now the cool thing when you're using cutter compensation, the machine tool takes care of all this stuff for you, and it can actually roll the tool sort of around these arcs and stuff like that. You don't have to do any of that extra math, all that stuff. There's some other reasons we like cutter compensation. We'll talk more about that later. It is almost time to go. There are groups. If you get a canvas, you're in a group. Before we meet next Thursday, the groups will have a group assignment. The groups will report back next Thursday, all 4 groups will report back the results of the group assignment. You're reporting back, and I'll put this in the assignment I post, but your reporting back will involve using a presentation and having one, if you need to, 2 people from the group standing up doing the presentation. So all the group collaborates in making the presentation, making the answers to the questions in the presentation. The presenter is presenting to the rest of the class what the group did. That's clear? The quizzes that we're going to do on Thursday next week, do them in the classroom because they require you to ask a pertinent question to the group about their project and give constructive feedback to the group about your experience. I suppose you could write down those answers on a piece of paper and go type it in later. But if you're doing it while we change presenters and stuff, then you're done with those quizzes and you don't have to do them later. And if you wait till later, you're going to forget something. Then you're going to have to go back and watch the video, and it's going to be a pain in the ass. So don't do that. Be prepared to answer those questions as you go, because that's your participation grade for that day, is answering those questions. And not all the groups will have the same thing to research. So I'm assigning some different things so that you come back and that we use you to teach each other the stuff. Because on Thursdays, I leave this place and I go teach another lecture directly. And so I'm going to take it easy on Thursdays and make you guys teach the class on Thursdays, and I'll teach the class on Mondays. Fair? All right, perfect. Thank you very much. Andrew's not here. You'll have to reach out to him online. Perfect. All right, so we need to